Hello, and welcome back to Aggressive Physics. Today's day 17, where we're going to analyze velocity versus time graphs. And in our previous day, we talked about displacement versus time graph, where we're going to graph the position of an object versus time. In this case, we're going to graph the velocity versus time. And what's different about velocity versus time is that we could have graphs that are not continuous. We could have a situation where the velocity changes rapidly and goes from a certain value to zero. So we can actually have graphs where we step down and create steps that look like continuous vertical lines along an entire graph. Now that could represent a completely different viewable graph in the displacement versus time. What's important is that a displacement versus time graph and a velocity versus time graph can represent the same motion of an object but have a completely different view. Now, the velocity versus time graph is probably the most versatile, and most of the time when you deal with a question about graphical analysis on the Regents or another assessment, you'll find that velocity versus time is the one that they use because you can do the most with a velocity versus time graph. Remember, there was only one thing we could do with displacement versus time, and that was to find the slope. Now, sometimes we had to make our own straight line, and that was when we drew a tangent line. And other times, the straight line was already there. The graph was straight. And if the graph's straight, we had a constant velocity. Now, when we have velocity versus time, we not only can analyze using the velocity by finding the slope, we can also use the area of the graph. So we have two different methods we can use, using the slope of velocity versus time and using the area of velocity versus time. So we have two math tools we're going to use. Now, once again, the shape of the velocity versus time graph can tell us what type of motion we have. 99% of the time, though, we're going to have straight line graphs. And that's because straight line velocity graphs represent uniform acceleration. And when we have uniform acceleration, as you remember, we can use the big five equations. Without uniform acceleration, those equations are out the window. We have changeable accelerations, and we have what we call a jerk. Now, we're not going to use jerked motion very often in this course, so 99% of the time the graphs will be straight line for velocity versus time. But we can have a curved graph in a conceptual question, and it'll just mean that you have a changing acceleration. But if you have a straight line velocity, you have a uniform acceleration. Now, you can have straight lines that are uphill, positive acceleration, straight lines that are flat, zero acceleration, and straight lines that are downhill, negative acceleration. Now, what mathematical tool can we use to find the acceleration? Well, that's going to be the slope. So if we have a straight line graph that goes uphill like the one you're seeing now, what you should realize is that represents a positive acceleration. You have to look at the labels, though, because as we move forward, the label could be displacement versus time, velocity versus time, or even acceleration versus time. So what you need to do is first read the label. And in this case, it says change in v, or velocity. Now, an uphill velocity means that we have a positive acceleration. And that positive acceleration could be whatever value the slope of that line is. So what you're going to need to do is utilize the slope equation. Now, in this case, the velocity is positive. The object did not start at rest. It was already moving when we started. With the displacement time graph of the same shape, it just represented it didn't start at the origin. In this case, the object was moving when we started the problem. So this could be an object that I dropped from a tall building 3 seconds after I dropped it. And I just called it 0 to start. Maybe someone was observing it past their window and then continued to view it as they were able to see it. Well, their window was below me and it was already moving. So this would have represented a object that's already moving. Now, this probably wouldn't be an object in free fall, though. Now, you may ask, well, how do I know that? Well, if this is a positive acceleration, it means that it's moving upward at a accelerated rate. Well, what direction is gravitational acceleration? Negative. So this would have to have a downhill slope. Well, that's a little too much semantics for now, but let's just talk about what we know about this one graph. As we move forward, the increasing velocity means that we have a faster speed up. Because we're going bigger and bigger in terms of the slope, we have a constant acceleration, yes, but an increasing velocity. Now, in order to find the slope, it's change in y over change in x. As we know, change in y is represented by change in v, and change in x is represented by change in t. Well, change in velocity over time is acceleration. A equals delta v over delta t. So the slope of a velocity graph can tell me the acceleration. Now, like I said, 99% of the graphs are going to be straight. So it'll either be a positive, a negative, or a zero acceleration. But what would you do if you had a curve? You could find the slope of a tangent. And since the acceleration changes, you would actually find the instantaneous acceleration. But like I said, the big five equations only work for uniform acceleration, so it's important to realize that most of the time you would be dealing with straight line velocity graphs. If not, though, you could handle it. Now, finding the slope of a tangent, finding the slope of the velocity graph in calculus is the second derivative of the position function or the first derivative of the velocity versus time function. So you would learn about that in calculus if you're taking calculus. If not, just store that in the back of your head for when you do take calculus and you realize that calculus is a way to describe motion a little quicker. You'll see that drawing graphs by hand takes time, but if you use calculus, it can be done a lot quicker. So there's ways that we use mathematics to make our lives easier, just like using a calculator made doing long division a little easier. But it was important to know how to do long division by hand first to understand what the calculator is doing, or else it becomes a mysterious object. The calculator isn't mysterious. It's just doing the work for you quicker. Now, here's the thing. We've only used slope so far. What about area? Our second math tool is finding the area. Now, we have a couple of options we have when we deal with our straight line velocity graphs. And the first option is a flat line. If the velocity is flat, it doesn't mean it's zero unless it's flat on the x-axis, which would be the origin, which would mean it has no velocity. In this case, it has a constant positive velocity. Now, if I find the slope of this shape underneath the curve is going to represent a rectangle. Well, how do we find the area of a rectangle? Base times height. But remember, the base isn't b. It's an actual physical characteristic. And in this case, it's time. The height isn't h. It's actually v. So if we multiply v times t, and it's a constant velocity because it's a flat line, well, that's v equals d over t. But we rearrange the equation. d equals v times t. So this graph, if we use the area, will actually allow us to find the displacement. If you find the slope of a velocity time graph, it gets the acceleration. If you find the area of a velocity time graph, it gets you the displacement. So depending upon what you're looking for, you'll either use the slope or you'll use the area. Now, we could have an area that is not a rectangle. In this case, it's a little more complex. And what we actually have is an uphill graph. It goes up, and we have a shape that would really be a trapezoid. But what we like to do in physics is actually simplify things. Despite what you may think, physics is about making things easier to understand. It's not about fancy terms and making ourselves seem smarter. It's actually a way to describe the universe simpler. So what we're going to do, instead of using a trapezoid, which is an equation that you may not remember from geometry, we're going to break it into two shapes. We're going to break it into a triangle, and we're going to break it into a rectangle. Now, the triangle is represented by 1/2 base times height. So the 1/2 is the fact that it's not a full triangle, or I'm sorry, a true rectangle. And instead what you're going to do is do 1/2 times the base, which is your time, times the height, which is your velocity. And remember, the reason we're using average is because it wasn't a constant. So that's why it's the 1/2. And you'll get the term for displacement for that section. Doing the area of the rectangle, you do base times height, and what you'll find is the base is t, the height is the velocity, and you'll be able to do base times height to get the displacement. Add those two together, you get the total displacement the object traveled during that time segment. Now what's interesting about this is that that yields us the equation for d equals vit plus 1/2 at squared in terms of the big five equations. So this graphical shape, if we use it to find the area, will actually find the equation that we're used to. Now the reason that equation exists is because we didn't start at the origin. If we actually started at rest, the VIT term would have disappeared. So a normal version will actually get us 1/2 AT squared. Now I'll show you that derivation when we do some sample problems in a little bit. But it's important to realize that the graphical analysis is no different than the mathematical. It's just a different point of view, a different way to look at it, a different frame of reference. Now that being said, we have area and we have the slope. And those are the two ways that we can look at the velocity versus time graph. Now, to talk about one more bit of information, what if we had a graph like the one we're looking at now? The graph represents an object's motion, and the graph kind of looks a little weird. It's not just staying in the positive direction, but it's going in the negative direction. Now this is the motion of an object that is very easy and very common for us to see. Can you figure out what it is? Think about it like this. The velocity is decreasing over time. It's 0. And then it's decreasing more negatively, which means it's getting bigger in a negative direction. Well, what type of object slows down, stops, and then speeds up again in another direction? Well, it happens to be an object being tossed up in the air and coming back down. As it goes up, the speed decreases, the positive velocity gets smaller and smaller, it stops at the top, and then it speeds up in the negative direction. Now, what do you notice about the slope of that line? It's constant. It's constantly negative. And what you would know is that if you actually found the slope of this graph and it was from real data, it should be negative 9.8 meters per second squared. And that's something we're going to look at in the lab. We're going to see if we can toss an object up in the air and come back down and find the acceleration of gravity. The graph should look just like this. It should be a downhill graph starting in the positive quadrant and going right down into the negative. But notice, where does the acceleration turn to 0? It never does. The acceleration of gravity is always negative 9.8 on this object. So this graph might help you realize that even at the top of the flight, the acceleration of the object is still negative 9.8 meters per second squared. I think we should look at some sample problems and find some areas of actual graphs that we can analyze, maybe find the slope of a few. But remember, there's only two math tools we can use for velocity. If you find the slope, it gets you acceleration. If you find the area, it gets you the displacement. And these graphs are actually the same, just a visual representation of the big five equations. A graph of velocity versus time is really equation 4 when we find the areas. D equals VIT plus 1/2 AT squared. All right, here are two different velocity versus time graphs. We have one on the left and one on the right. The one on the left represents an increasing velocity in a positive direction. The slope would be the acceleration. In this case, it would have a positive acceleration. It would also be, because the slope is constant throughout, uniform acceleration. From the looks of things, this object started at rest and then traveled at an increasing rate of velocity throughout. Now, if we label that line A, we can just compare without numbers the difference between that and line B. Now, according to this, just from the observation of the two lines, we know that B has a steeper slope. Therefore, I'll use a math symbol, the therefore symbol. B is accelerating at a higher rate. So the acceleration of B is greater than the acceleration of A. Now, on the right, you're looking at a jerk. Now, stop looking next to you if you're sitting in the room with someone else. Don't look in the mirror, because that's not very nice. That's not good self-esteem. This is actually a graph of a jerk. So there's a mathematical representation of a jerk right here. And the reason I know that's a jerk is because the acceleration, which is the slope of tangent lines, is changing. In fact, the acceleration is increasing as I go from the origin along the rest of the graph. So if you have a curved velocity versus time graph, then it is a jerk, which is just a fancy word for a changing acceleration, a non-uniform acceleration. Now, the reason we don't deal with jerks in this class very often is the fact that the big five equations have to use uniform acceleration. So if you don't have uniform acceleration, you can't use the equations. In this case, this would be more of a qualitative question. What is happening to the acceleration? And you'd have to recognize that the acceleration is changing in this example. Now, these are how we could deal with the velocity time graph dealing with slope. The slope, as you know, is change in y over change in x, or in this case, change in v, put up here, change in over change in t, which happens to equal the acceleration. So that's the a, and that's why the slope equals the acceleration. All right, let's move on to the area next. Okay, if we have this graph, what we can see from it is that we have an increasing velocity for the first segment. We'll just say from 0 to A. And then for the second segment to B, it's traveling at a constant velocity. So this part is accelerating, and this part is not accelerating. It's going at a constant velocity. Now, if we were to find the slopes, this would have a positive value, change in y, change in x. This would have a 0 value. So acceleration is 0, acceleration is positive. And we could do that mathematically. But if we're looking for the area, that's going to represent, in this case, the shape here, which is a trapezoid. And then over here, it would represent, I'll just use a different direction for my lines, the rectangle. Now, the problem with the trapezoid is I don't remember what the equation is for the area of a trapezoid. So what I do is I break this into a triangle and a rectangle. So if I wanted to find what is my displacement from 0 to point B, I would find the area of the triangle, area of this rectangle, area of this rectangle, and I would add them together. If you're above the axis, your displacement is positive. So you have a positive displacement above the axis. If you're below the axis, it's negative. So you could have a situation where some of your areas are above and some of your areas are below. Now, what that would look like, if I just extend this line down here, maybe we have a negative velocity and then a 0 velocity for the rest. And this negative velocity goes to point C. Well, the way that would happen is an object speeds up, is traveling along, and then this is where it's not realistic, but it drops to a negative velocity instantaneously. And the way we could do that is I guess the best way would be you take your car, you're going forward, you're cruising along, and then all of a sudden you switch to reverse while you're still moving, and it immediately shifts to reverse. Then you travel a constant backwards velocity in negative cruise control, let's say. Now, that's not realistic. You would have some kind of curve here. There would be some kind of jerk motion, I would imagine. However, just for this example, if we then found the area of this section, this would have a negative value. But just by looking at the areas under the curves here, and I know straight lines, we still call them curves, but the area under the graphs, they are bigger in the positive direction, or the positive displacement, and smaller in the negative, because this rectangle, if anything, is about the size of these two objects in total. And that's just by look, visually. So a conceptual question that could be asked without numbers would be, is the displacement at the end of the journey from 0 to C positive or negative? And just by seeing that there's more space under here, you could say or conclude that the net displacement would be positive. We end up away from home more positively than negatively. But in this case, the shapes help guide us. And we're going to stick to typically shapes that are triangles or rectangles in this course. You could deal with shapes that are curved, but we're getting into more calculus. And really, you could deal with a curve just with estimation. But if you wanted to find the area under a curve that is literally a curve, here's your VT graph, and you want to find the area under that, what you would need to do is use calculus. You'd actually have to know the function for this and then integrate over 0 to point, we'll just call it 2, 0 to 2. And if you integrate under that, calculus can actually find the area under all the curves and nuances. You don't need a fancy equation. You don't need anything like that. It's just using integration. Well, I guess which is a fancy equation.